Hi there, welcome to the presentation of Talek, a private group messaging system. We know that group messaging is everywhere. We have applications today like chats, news feeds, calendars, and even games. There are a lot of these applications that can be modeled as group messaging systems. And in typical messaging systems, users deposit messages into a log, and users can subscribe to either message or event. They are typically facilitated by some kind of cloud service and can be regarded as untrusted environment. Today we have end-to-end encryption. It is a well-known problem, and there's a well-known set of solutions for encrypting the message end-to-end, such that the cloud service has no way of reading the contents of the messages themselves. And some examples of this would be something like WhatsApp and iMessage. Messaging application depends on the cloud service to exchange data. So the server can eyewitness the communication patterns between the users. A curious cloud can still log all of the network access and be able to do some statistical analysis on the message workload itself. And the communication patterns themselves become exposed to the cloud service, can make the cloud service determine whether the users are sharing data, who is talking to who, and when the traffic is set, and how much data is set, and sometimes potentially even allowing the adversary to infer the contents of the communication itself. So, protecting metadata is also very important. And the Talek is a private group messaging system for sharing data through the untrusted clouds. The goal is to hide both the contents of the messages as well as the communication patterns among the users. Talek's goal is to hide both the contents of the message and the communication patterns among users. Talek makes all this practical using a set of techniques we call the oblivious logging and private notification and so on. The security goal is that of indistinguishability. In the paper, it is formally defined as access sequence indistinguishability, and informally, what that means is that two access sequences, usually consisting of reads and writes of arbitrary length from the client, they should look indistinguishable to the adversary. So to achieve the security goals, Talek relies on the private information retrieval and propose a oblivious logging scheme. To achieve the good performance and minimize the server-side storage, Talek introduced a novel use of logged tuple hashing and support for private notifications. Then we introduced the notion private information retrieval, PIR for short. Abstractly, PIR allows a client to retrieve the record from the database, which is contained by many servers, without the server learning which record was retrieved. We can see the example here. When a client want to read a chosen block, like the second block from the three servers, the client generates a vector which is all zero except at index beta is 1. Then several request vectors are generated, at random, and these vectors are set to corresponding server to get the response. Then client can get retrieve result by taking the straw of all the response together. In this way, each server retrieves a vector, and the index vector is indistinguishable from the random generated request vectors. So client can restore the desired block without any server noticing which block the client retrieves. Before we go to the design of the Talek, we need to clarify the model. It consists of a finite set of servers and clients, and all parties are stateful. Client state consists of logs and the read and write queue. Server state consists of a log and a hash table for storage. And the overall design system consists of the subroutines like this. For the client, real-write takes a log handle a message with the sequence number as input and outputs a write request one per server. The fake write generates a set of random dummy write requests, one for each server. And the real read takes a log handle and a sequence number as input and outputs the reading request one per server. The freak read generates a set of random dummy read requests, one for each server. The get update retrieves the global interest vector for the servers. Oh well, the interest vector we mentioned here contains the information like log handle message sequence number for all messages currently on the server. Then we will discuss it later in our presentations. And for servers, there's process write to process the incoming write request for client and update the server's internal state. The process read gives replies of the read request and returns the replies value. The process update generates a global interest vector, which is a union of the interest vector each server. Then we see the definition of the security game. The security goal of Talek is to achieve access sequence indistinguishability. And the security game is defined like this. The adversary here is a polynomial time 1. It controls the network, all servers except one, and it also controls a polynomial number of clients. The challenger eliminates the honest clients and servers. And in this game, the adversary specifies any two actions for each legitimate client to take, sequence 0 and sequence 1. And the challenger choose a random bit B and let the client execute one of the two actions based on B. And the adversary can then choose new actions for the legitimate clients or have its malicious clients or servers take actions. The game continues until the adversary produces a guess for the value of B. Then if the adversary does no better than the random choice, say the probability to make a right guess plus 1 over 2 is a negligible value, which means the adversary cannot determine which users can access the same log. And that we called access sequence indistinguishability in this game. Then we look into the core part. the designer, clients, and the service. A set of techniques are used here to achieve the security goal and good performance. For client design, the security goal requires all users to behave identically from the perspective of any service or any collating set of all servers except one. Decoupling is the key step. The Talek decouples the real rate from the network request rate. The client here maintains an internal read queue and internal write queue. It links their messaging application to the client uh, to the Talek client service. Whenever a request is issued by the messaging application, Talek places its payload on the corresponding internal queue. For the decoupling process, to decouple the real rate from the network rate, the Talek client library issues a dummy request. It issues a frank write if the write queue is empty, and it issues a fake read if the read queue is empty. The dummy requests should be indistinguishable from the real ones. To achieve this goal, the Talek defines a global fixed message size and the split and paired messages, then encrypted with a symmetric encryption scheme. For servers, to achieve good performance, each server stores the latest messages, while garbage collecting the oldest. To effectively pack messages into a compact data structure and also make it compatible with the private information retrieval, Talek is a block token hashing table. Logs and logs here are spread over the hash table and read using the private information retrieval. And then we will see some details of the block token hashing table. In the Cocoa hash table, each client writes requests specified to pursue random buckets, and the message can be inserted here. For the read process, when the client performs a read request, the hash table is treated as a private information retrieval database, with each hash bucket as an entry. And the client uses a private information retrieval to retrieve an entry hash bucket without revealing to the server. For the write process, the Cocoa hash is a history dependent and the private information retrieval also requires the consistency of recipes across all servers. So we must ensure that all writes are inserted into the same order. Talek addressed this with the serialized private information retrieval technique. Then when the Talek client library decodes a message with its sequence number from this internal write queue, it computes two indexes and encrypts its data. The indexes beta 1, beta 2, and the data are set to the server. If the internal write queue is empty, it chooses two indexes randomly and compute a dummy encrypted data For example, here it choose all zeros ones. And for each server, they deals with the write request follow this algorithm. It tries to insert the received data into either of the bucket, beta 1 and beta 2. If there's a space, the data is inserted successfully, but if both buckets are full, um, they use a grade random seeds here and to derive an index and insert to this position anyway. That is to say, if it's not empty, um, inject the entry and insert anyway. Then we will see the reading process with the private information retrieval technique. We can see an internal read queue here. And if the queue is not empty, we can decode an element from it. That is to say, if the queue is not empty, the Talek client library decodes a log read at a sequence num from its internal read queue. Then it can generate a read request using the following algorithm listed here. When the queue is not empty, the client can generate the read request real read. Firstly, the library performs a private information retrieval read for the first position cocoa location. The first position cocoa location can be computed as a Purcell random function takes the case as 1 as input and the sequence num as input and outputs the position beta 1. It's the first cocoa location from the cocoa hashing table, and and then the library attempts to decrypt error message in the bucket at this position beta 1. If the decryption succeeds and matches the sequence num, then the message will be returned to the application. If the decryption is not succeed and does not or does not match any given sequence num, and we will try the second cocoa location by calculating the Purcell random function, takes the K2 as input and the sequence num as input, and outputs the beta 2 as the second cocoa location in the cocoa hashing table. And then we will repeat this process, decrypt messages in the bucket beta 1 and check whether the decryption succeeds or the result matches the sequence num. And if all this passed, we can return the message. As we introduced before, the Talek uses a coupling technique, and it's just decouple the real rate from the network request rate. We know it fails to hide which the users read the answers messages. To achieve the security goal, Talek used the private information retrieval to retrieve the record privately, without any server noticing which clients retrieve which record. But the private information retrieval alone does not explain the writing process. Like, it does not explain how to write to servers. It also does not explain how to let communication patterns know which message to read. if they want to read something and there's something new. So Talek designed a component called oblivious logging. We will introduce the oblivious logging here. The Talek issues writes to particular random location on each server, and the sequence of writes locations is determined by applying a particular random function between the logs write and the writers. As we see here, as we see before, this is implemented by the Cocoa hashing table. The readers follows the pseudo-random derivation and derives the sequence of the location in order to retrieve messages. And overall, the server simply say a series of seemingly random writes and the private information retrieval protected reads. In this way, it totally hides the communication patterns between the writer and the readers. Then we focus on the private notification. The private notification is a very important component for the Talek. It helps Talek achieve good performance. The private notification allows users to determine when new messages have been published to a log without revealing the list of all the logs they subscribed before. The main idea is to detach reads from the notifications. In this way, it can reduce the reads and achieve high efficiency. Talek uses the interest vector and the global interest vector here. The interest vector maintained by the client and global interest vector maintained by the servers. They both play important roles. Let's focus on the interest vector. It is implemented by the block filter, so the insertion and check using the block filter is very efficient. The interest vector privately encodes the log handle and the message sequence number for use. For the server, each server maintains a global interest vector. It's a union. It's a union of the interest vector, and it's globally. It encodes log handle message sequence number for all the messages on the servers. Then the server can periodically assign the global interest vector and exchange the signatures in a multi-signature scheme. The multi-signature scheme we mentioned here is an interesting topic, and if you are interested in it, you can search for more details. The client then can verify the received global vector using its signature and check whether it passed, whether it's valid, and or it's from the adversary. The security of the private notification relies on the cryptography hash functions using the Bloom filter. That is to say, each interest vector provides a knowledgeable advantages in the indistinguishable security game if the hash function is secure in the Bloom filter. In this paper, Talek is tested using some realistic workloads. and is evaluated by some cost and performance, like CPU cost of operation for clients for the service, and the cost of caller traffic, the cost of storage for clients and service, the end-to-end latency and the throughput in many aspects. And the static shows that a Talek scheme achieves good performance in many ways. The cost of CPU clients, the cost of server CPU, uh, and the server storage cost and network cost are are all reasonable. And compared with other schemes, Talek also performs well in the read process and write process. The storage and the networks also performs fine. It achieves good performance overall under its security goal. Talek explored a new point in the design space of private group messaging. It proposed a very strong security guarantee based on access sequence indistinguishability. Users' behavior seem identical from the perspective of any server or any collating set of all servers except one, and it coped with and only slightly weakened antitrust model. Talek incorporates a series of design decisions and new optimizations, including the private information retrieval based on the blocked Cocoa hashing and the theorized private information retrieval technique, the private notifications that achieve good performance for the Talek, and the oblivious logging. Together, the design supports strong performance for realistic workloads as the tested static shows. I think for security, we can further think about the security of Talk in the antitrust threat model because it's currently considered in the slightly weakened one. And to achieve good performance, I think data deduplication can be considered. It can further saving the storage cost, and for some application that can be treated as a messaging system like the file transferring system, um, we can store only the unique data and refer the redundant data to the only one physical copy. It can become very efficient. But there's always a trade-off between the good performance and the storage cost. We need to test it maybe in the experiment and decide a better solution. What's more, um, we can think about how to exploit the idle time. It's also an interesting point. I think the idle time can be used to do something like pre-computation. Well, that's all of the presentation. Thank you for listening. And if you are interested in the group messaging system, we can have some discussions. Thank you and goodbye.